Hey everyone, welcome back to the channel. Today we're looking at the 4 equations of motion. And just like everything else in this course, we're not going to memorize them. We're going to derive every single one, starting from something you already understand. If you remember, we defined acceleration as the rate of change of velocity. From that definition, we got the equation A equals v minus u over t. Here, v is the final velocity, u is the initial velocity, and t is the time taken. We're going to use this one expression as the starting point for everything that follows. Let's set up a single example and use it throughout. Imagine an object initially moving at 10 meters per second. That's our initial velocity, so u equals 10. And since this is the start, t equals 0. After some time, the object speeds up to 40 meters per second. That's our final velocity, so v equals 40. Let's say this change happens over 10 seconds, so t equals 10. I'm choosing these numbers because they keep the arithmetic simple. The method is what matters here, not the numbers themselves. Now let's plot this on a graph. Velocity on the vertical axis, time on the horizontal axis. Remember, velocity is measured in meters per second and time in seconds. At t equals 0, the velocity is 10. At t equals 10, the velocity is 40. Since the object accelerates at a constant rate, the line connecting these 2 points is straight. Look at the gradient of this line. To find the gradient, you take 2 points and calculate the change in the y value divided by the change in the x value. In our case, the y value is velocity, so the change in y is the change in velocity. The x value is time, so the change in x is the change in time. So the gradient is delta v over delta t, and that's exactly the definition of acceleration we started with. The gradient of a velocity-time graph gives you acceleration. That's not a coincidence. It falls directly out of what acceleration means. Now let's look at something else on this same graph, the area underneath the line, between the line and the time axis. Look at the shape this area makes. It's a trapezium, 2 parallel sides and a perpendicular height between them. You may already know the formula for the area of a trapezium. If the 2 parallel sides are A and B, and the height is h, the area is a plus b over 2 times h. In our graph, the 2 parallel sides are the 2 velocity values, 10 and 40, and the height is the time, 10 seconds. So the area is 10 plus 40 over 2 times 10 equals 25 times 10 equals 250. 250 what, though? Let's find out by working through the units instead of the numbers. The 2 parallel sides are both measured in meters per second. Adding 2 quantities in meters per second still gives you meters per second. The height is measured in seconds, and the divide by 2 has no unit at all, since 2 is just a number, not a physical quantity. So we're left with meters per second multiplied by seconds. The seconds cancel, leaving meters. 250 meters. And a quantity measured in meters describing motion is a displacement. So what we've just shown is this. The area under a velocity-time graph gives you displacement. Let's write this generally, using symbols instead of numbers. The 2 parallel sides are u and v, and the height is t. So the area, which is displacement, s, is s equals u plus v over 2 times t. That's our second equation. Combined with the one we already had, equation 1, v equals u plus a t. Equation 2, s equals u plus v over 2 times t. 2 equations down. Now we're going to use these 2 to derive 2 more, purely through algebra. Take equation 2, s equals u plus v, divided by 2 times t. We're going to replace v with what equation 1 tells us v equals, u plus at. S equals u plus at, divided by 2 times t. Simplify inside the brackets. S equals 2u plus at divide by 2 times t. Split this into two separate terms. S equals ut plus half at squared. That's our third equation. For our fourth equation, we're going to eliminate time instead. Start with equation 1. V equals u plus at. Rearrange to solve for t. V minus u equals at. T equals v minus u over a. Now substitute this expression for t into equation 2. S equals u plus v over 2 times v minus u over a. Multiply the numerators together. Notice that u plus v times v minus u is a difference of squares, which simplifies to v squared minus u squared. So s equals v squared minus u squared over 2a. Cross-multiply to clear the fraction. 2as equals v squared minus u squared. Rearranged. V squared equals u squared plus 2as. That's our fourth and final equation. So there we have it, 4 equations of motion. V equals u plus at. S equals u plus v over 2 times t. S equals ut plus 1/2 a t squared. V squared equals u squared plus 2as. Together, these are known as the SUVAT equations, named after the 5 variables they contain: S, U, V, A, and T. But there is one condition you need to lock in before you use any of them, and I want to say this as clearly as I possibly can. These equations only work when acceleration is constant. If acceleration is changing throughout the motion, none of these 4 equations apply. This isn't a minor detail. It's the single most important condition attached to everything we've just derived. Now let's look at motion graphs. There are 3 types we're going to work through: displacement time graphs, velocity time graphs, and acceleration time graphs. For each of these 3 graph types, we're going to examine the same 4 motion scenarios: a stationary object, an object moving at constant velocity, an object undergoing constant acceleration, and an object undergoing constant deceleration. Let's start with a stationary object. If an object is stationary, its displacement doesn't change over time. So the displacement time graph is a horizontal line, parallel to the time axis. Since the object isn't moving, there's no rate of change of displacement. And rate of change of displacement is exactly what velocity is. If displacement isn't changing, velocity must be 0 throughout. So the velocity time graph looks like this. And since a stationary object has no velocity at all, there's certainly no change in velocity. So there's no acceleration either. The acceleration time graph looks the same way. Now let's move to constant velocity. When an object moves at constant velocity, its displacement increases steadily over time. So the displacement time graph has a constant, non-zero gradient, a straight, diagonal line. Since the velocity itself is constant, the velocity time graph is a horizontal line, but this time sitting above the time axis, at whatever the constant velocity value is, rather than on the axis itself. And because the velocity isn't changing, the change in velocity is 0, which means acceleration is 0 throughout. So the acceleration time graph looks like this. Now here's something worth noticing. Look at the acceleration time graphs for these first 2 scenarios, stationary and constant velocity. They're identical. Both show a flat line at 0. This tells us something important. You cannot determine from an acceleration time graph alone whether an object is stationary or moving at constant velocity. Both produce exactly the same acceleration graph. You'd need to look at the velocity time or displacement time graph to tell the difference. Next, constant acceleration. For the displacement time graph, the gradient is now increasing over time. The curve gets steeper and steeper. This makes sense. If velocity is increasing, displacement should accumulate faster and faster. For the velocity time graph, since velocity is increasing at a steady rate, we get a straight line with a constant positive gradient. And since the acceleration itself is constant, the acceleration time graph is a horizontal line, parallel to the time axis, sitting at whatever the constant acceleration value is. Finally, constant deceleration. For the displacement time graph, the gradient is decreasing over time. I want to be precise about this. The gradient is reducing. It is not necessarily negative. The object could still be moving forward, just slowing down, which means displacement is still increasing, just more and more slowly. For the velocity time graph, we get a straight line with a negative gradient. The velocity is decreasing over time. And for the acceleration time graph, we get a horizontal line again, but this time below the time axis, because deceleration is simply negative acceleration. Out of these three graph types, the velocity time graph is the most useful because it gives us information in both directions, about displacement and about acceleration from the same single graph. If you recall from the previous section, when we derived the equations of motion, we used the velocity time graph that looked like this one over here, and we calculated the gradient of the graph and the area underneath it. The gradient of that graph gave us acceleration. The area underneath gave us the change in displacement, delta S. Now let's generalize this properly because each of the three graph types carries different information in its gradient and in its area, and some of that information simply isn't meaningful at all. For a displacement time graph, the gradient gives you velocity. The area under the graph, however, doesn't correspond to any meaningful physical quantity. For an acceleration time graph, the gradient doesn't give you anything meaningful. But the area under the graph gives you the change in velocity, delta V. In other words, final velocity minus initial velocity. And that's the four equations of motion and how to read motion graphs. Everything on the sheet you're looking at right now. Grab it for free, along with a full worksheet and worked solutions. Links in the description. If this helped things click a little better, a like or a subscribe genuinely helps this channel grow. But either way, I'm glad you stuck around. Quick bonus before we wrap up. If you're also taking math analysis and approaches, SL or HL, you're going to meet these exact same equations again, just written differently. Velocity is the derivative of displacement. Acceleration is the derivative of velocity. And if you integrate a constant acceleration twice, you get v equals u plus at, and s equals ut plus half at squared, right back out. Same equations, built from calculus instead of algebra. Just remember, that only works because acceleration is constant. The moment it isn't, you're back to differentiating and integrating directly. And if you're taking Math AI instead, this particular connection doesn't apply. This one's an AA topic. Next up, motion under gravity and projectiles. And that would be the end of kinematics, for the time being. See you there.